All right, welcome back. Now here we are in Module 2. You've got a quiz that you'll complete in this module that relates to what was covered in Module 1. What we'll talk about in this module can also help you with that quiz, but you don't have to go through all the materials before you take the quiz. Okay, with that said, in this session, we're going to dive into one of the most essential components of any IoT system, the sensors. All right. So sensors serve as the eyes and the ears of IoT devices, and they enable them to observe the environment, gather data, and respond accordingly. Now, let's begin by exploring what sensors are and why they're fundamental to IoT. So at their core, sensors are devices that detect and measure physical properties such as temperature, light, pressure, motion, gas levels, humidity, and more. Once these properties are detected, the sensor converts them into an electronic or an electrical signal that can be processed, stored, or transmitted. Now, sensors are typically classified into two categories. We've got analog and we've got digital. Analog sensors produce a continuous signal proportional to the physical quantity that they're measuring. Let's say a thermostat or a temperature sensor, for example. That might have output at a voltage that increases linearly with rising temperature. So the hotter this thing gets, the output voltage increases. Digital sensors, on the other hand, they produce discrete signals, often in the form of binary data, indicating specific states of measurement. Temperature is this. It sends the data, the number, if you will. These are particularly useful in systems where high noise, immunity, and accurate, fast readings are needed. Now, IoT sensors vary significantly depending on the application. Some common sensor types include, let's say, temperature sensors. We use them in HVAC systems, refrigerators, environmental monitoring. Your thermostat in the house controls the AC unit. That's a temperature sensor. Proximity sensors found in security systems and mobile phones. Accelerometers used in fitness trackers, smartphones, and industrial vibration monitoring. Light sensors enable smart lighting system to adjust brightness based on ambient light. And then there's gas sensors. They monitor CO2, smoke, and hazardous gases in smart homes or in industrial environments. Now, to function properly within an IoT system, these sensors must communicate with a central controller or a data processor. That's where interfacing protocols they come into play. So I'll leave that here. So let's talk about these interfacing protocols. I scrolled way down the page to get to the interfacing protocols. Between where we are now and where we left off, before I paused for a little bit, were a variety of different types and examples of different sensors. So there's several standard protocols that are used for this communication. Now we've got I2C, you see in the upper right corner. That's inter-integrated circuit. It's a synchronous multi-master, multi-slave protocol, often used when multiple sensors need to communicate with a microcontroller using just two wires. one for data, SDA, and one for clock, SCL. It's great for short distance communication in an embedded system. There's one protocol. Now we've also got SPI we see below it, which is Serial Peripheral Interface. Now it's another synchronous protocol that's faster than I2C and uses more wires. It typically involves a master device and one or more slaves and allows for full duplex data exchange. As we move around the circle, we've got UART, Universal Asynchronous Receiver Transmitter. It's a simple asynchronous protocol that allows two devices to communicate over serial ports using a TX and RX line. UART is useful when sensor data doesn't need to be transferred in large volumes or at high speeds. Now, from there, we've got one-wire protocol. Now, this is used for simple low-speed data communication, often temperature sensors, like a DS18B20. As its name applies, it uses just a single data line plus ground. Now, the choice of protocol depends on several factors, including the number of sensors that are going to be connected, the required communication speed, distance between the sensor and the processor, power consumption constraints, budget and design complexity. Now, let's look at sensor integration for a little bit and how these protocols are implemented in practice. So when connecting a sensor to a microcontroller, physical interfacing is the first step. This means ensuring the sensor's voltage levels and signal types are compatible with the board. For example, many IoT microcontrollers like the Arduino operate at 5 volts, while some sensors use 3.3 volt logic. Logic level shifters or voltage dividers are often needed to match levels safely. So we've got to make sure that all these connections match up. If they don't, we've got to find something to get it right, and we've got level shifters can do that for us. So once the physical connection is in place, software integration begins. Microcontrollers often use sensor libraries to simplify the communication process. These libraries handle protocol-specific functions like reading and writing bytes, interpreting signals, converting raw data into readable values. Let's briefly explore an example. Let's say we want to interface a temperature sensor using I2C. We connect the sensor's SDA and SCL lines. Remember we said it had on I2C there's 2 lines to the corresponding pins on the microcontroller. In our microcontroller code, we initialize the I2C bus. We use a sensor library that abstracts the low-level communication, allowing us to retrieve the temperature with a simple function call. We essentially, as I like to call it, we outsource the work to a function. That function does the work for us. Okay. The process, hardware connection followed by software configuration, is the heart of sensor interfacing in IoT systems. Now let's discuss power considerations, because power is a big deal. I said that they don't use a lot, but they do use power. So many IoT devices are battery powered. Power efficiency is crucial. Some of the key practices to reduce power usage include choosing sensors with sleep or low power modes, using interrupt-driven readings instead of continuous polling, minimizing sensor activation time, selecting protocols like I2C or one wire, which typically consume less power than high-speed SP1. We should also consider the calibration and accuracy. No sensor is perfect. Environmental conditions, component quality, and age can all affect accuracy. To mitigate this, manufacturers often include calibration data. And in calibration applications, real-time recalibration might be required. So signal filtering and averaging are also commonly used in software so that we can smooth out noisy readings. The last thing we're going to deal with is trends and future developments in IoT sensing. So as sensors continue to evolve, we're seeing innovations like microelectric mechanical systems, MEMS, and they allow highly compact and integrated sensors. Smart sensors with built-in processing capabilities to reduce load on the central controller. Energy harvesting sensors that generate power from light, vibration, or heat. These advances are enabling new possibilities in health monitoring, environmental sensing, industrial automation, where sensors can not only collect data, but also pre-process it locally. So to wrap things up, sensors are the cornerstone of IoT. They enable data collection from the physical world. Interfacing protocols like I2C, SPI, UART allows sensors to communicate with microcontrollers. Choosing the right sensor and protocol requires balancing complexity, power, cost, and accuracy. Future trends are pushing sensors to be smarter, smaller, and more autonomous. Understanding sensors and how to interface with them is foundational for building reliable, scalable, and efficient IoT systems. In our upcoming modules, we'll explore how to program and deploy these systems in real-world environments. So I'll see you in the next module. Make sure you get the quiz knocked out here in Module 2 before we move into Module 3.